Okay, so we're reviewing for your midterm exam here. And our plan is to review limits today and to review derivatives tomorrow. My part is to provide you with a big picture and to let you know what you will need to know. And I've done that in the two handouts that you have before you. Your part is to be competent, and in particular, that means to know the language of the definitions and theorems, be able to draw pictures of those definitions and theorems. For example, for your sign of f prime theorem, the language is if f prime is positive on a to b, then f is increasing on a to b, and f prime is negative on a to b, then f is decreasing. And so you should be able to draw some picture that illustrates that with a function like so, where f prime is positive on this interval, and f prime is negative on this interval, and there it is. Yes? Okay. So then, finally, you want to be able to apply the definitions and theorems to various situations. For example, with curve sketching or something like that. Okay. Now, let's jump right in. We're talking today about limits. So the first question is, what is a limit? And our definition, we'll use the color scheme that we have been using, which is, I put everything in red. That is literal language for you. The limit, as x goes to c, f of x equals L, means that f of x is arbitrarily close to L. When x is close to c. Excuse me. Got distracted by a thought. Close to, but not equal to c. Wow. And the but not equal to is very important because we do not wish to consider what happens at x equals c. What happens at x equals c is not relevant with regard to the limit. So a picture that we could draw for this situation could be a function that looks something like this. And maybe there's a point up here somewhere. And we could say that while f of c is equal to m, nevertheless, the limit as x goes to c of f is equal to L. Why? Because no matter how close I wish to get to L, I can find a neighborhood around c so that all of the y values for x's around c fit in my neighborhood around L. That's the basic picture that we have right here. And the fact that f of c is equal to m, that plays no bearing on this. So that's what it means for the limit to be equal to a value. Now the question is, how do we find those limits? And we spent a fair amount of time finding those limits with various methods. We want to consider analytic methods. What? We want to consider graphical methods, and we want to consider numerical methods. And all of you should be good at all of these because different circumstances will require them. But in all of these methods, the analytical, the graphical, numerical, we're going to go back to that definition. F of x is arbitrarily close to L when x is close to, but not equal to, c. So with regard to the analytic methods, we had multiple ones. First of all, we had the limit properties. The limit properties are slow but thorough and For that reason, you should use the limit properties only if it's necessary. Really, only if I say use the limit properties. But those limit properties were the basic ones, such as the constant multiple rule for limits. The limit as x goes to c of k times f of x is the same as k times the limit as x goes to c of f of x. Or the quotient rule. The limit as x goes to c of f of x over g of x is the same as the limit as x goes to c of f divided by the limit as x goes to c of g. Unless what happens? What's the one way that
x goes to c, g of x is not equal to 0.
Yes. We need to put in that important qualification that we cannot divide by 0. If that is the case, that the limit as the denominator as x goes to c is 0, then we will have to consider other theorems rather than the limit properties. So in addition to the constant multiple rule, we had in the quotient rule, we had sum rule, power rule, product rule, difference rule. We had a constant rule and an x rule, or a linear function rule. I'll just write linear function rule. And you should look all those up in your notes or the book to make sure that you got the strict legal language of those. Just as a quick example of use, if you have to evaluate the limit as x goes to 1 of root x plus 3, then we would consider, first of all, that this function is x plus 3 to the 1/2 power, so that we can use the power rule to rewrite, like so. Then we could use the sum rule. And finally, we can evaluate each of these limits directly, just like so. Also, you may have noticed a linear function just sitting here, so there's that. Well, in addition to the limit properties, we also had 3 special limits. And you guys can tell me their values. The limit as x goes to 0 of sine x over x is. The limit as x goes to 0 of 1 minus cosine x over x is. And the limit as x goes to 0 of e to the x minus 1 over x is. You do not need to worry about proofs for the top one or the bottom one. The proof for the top we did, but is fairly complicated. The proof for the bottom one, we really don't have the machinery to do. But the middle one is a fairly easy proof, and everybody needs to know how that proof goes. Because it illustrates the technique of rationalizing. In this particular case, we can multiply top and bottom by 1 plus cosine x. And when we do, what do I get when I multiply 1 minus cosine x times 1 plus cosine x? 1 minus. Yep. So, which is the same as? Yes. Let me make a recommendation to you at this point, because I see some of you furiously scribbling. Let me take care of getting the notes down, and you guys get your head out of your notes a little bit and free up your mind to ask questions and think about what's happening, okay? And I'll put these notes out and give you a copy. So now we observe this limit right here, and we see things that remind us of our special limit right here. And so we handle that by peeling off the necessary factors, sine x in the top and x in the bottom, and we let the other factors do what they're going to do. Sine x in the top and 1 plus cosine x in the bottom. This limit goes to 1. This limit goes to, let's see here, sine of 0 is 0, and sine is a continuous function, so its limit equals its function value. And cosine is a continuous function. Cosine of 0 is 1, so that this limit goes to 0 divided by 2, which is the same as 0 times 1 is 0, and we're done. So this proof is one that everybody needs to know how to do. How are we doing so far? Now, we would love to be able to evaluate limits simply by direct substitution where possible. And the general answer to that question is, if f is continuous at x equals c, then the limit is the same as the function value. That's what it means to be continuous, which means that I can evaluate that limit by direct substitution for any continuous function. But in particular, we have two classes of functions that are always continuous. Polynomial functions. If p is a polynomial, what is a polynomial? What is a polynomial function? Straight line. A straight line is a polynomial, but not all polynomials are straight lines. What's that? You guys have awesome. A polynomial is going to be the sum of terms consisting of coefficients times powers of x, and those powers are non-negative integers. So a polynomial is going to be in the form an x to the n plus an minus 1x to the n minus 1 all the way down to a1x plus a0. So if p of x is in this form, then automatically the limit as x goes to c of p of x is the same as simply p of c. Why? Because my function is continuous. How do I know? Because if I apply my limit properties to this and use sum rule, constant multiple rule, power rule, then I get p of c. So for example, the limit as x goes to 2 of 3 minus 4x squared plus 6x cubed. Unless for some reason I must, there is no need for me to walk through the process of limit properties here. I see that this is a polynomial, and I say, let's directly substitute. That is 3 minus 16 plus 6 times 8 is 48, which is going to be equal to 35. In the other class, I dorked up the arithmetic. Likewise, our rational function theorem allows us to directly substitute in the case of rational functions. and q of x are polynomials, then the limit as x goes to c of p over q is the same as p of c over q of c, as long as
Q of C non-zero.
q of c is not 0. And the reason for this is fairly simple. Apply the quotient rule. Now I have the limits of two polynomials, and I apply the polynomial function theorem, and we're done. So this allows us to do direct substitution. What about that case where q of c is equal to 0? In the case where q of c is equal to 0, then we cannot use direct substitution, and we have to use other tools. And so this leads us to a slogan, and our slogan is, check the form before you go evaluating. And in particular, if we happen to have a form of 0 over 0, we call this the indeterminate form. And that indeterminate form is an indicator that we have a common factor somewhere that can be canceled. And so for that, we would make use probably of the alias theorem. If f and g are the same, except that x equals c, then their limits are the same as well. And so we might use it in this fashion. What is the limit as x goes to 2 of x squared minus 4 over x minus 2? We consider this limit, and the very first thing we do is check that form. And what is that form?
0 over 0.
Yep. And where will I put the form 0 over 0? Off to the left, out of the way of my equal sign here. And this indicates to me that there is a common factor that can probably be canceled. And lo and behold, I find it by factoring. And when I cancel right here, this is the moment where I am appealing to the alias theorem, because the function x plus 2 is the same as the function x squared minus 4 over x minus 2, except at x equals 2. At x equals 2, this function doesn't exist. At x equals 2, this function has a value of 4. Therefore, their limits are the same. Good? Mm-hmm.
Except x equals 2x minus 4 over x equals 2x.
This function
And
and the function x plus 2 are the same functions, except at x equals 2. When x equals 2, this function doesn't exist. When x equals 2, x plus 2 does.
so except x equals 2 there would.
Yes, which means they fit the condition for the alias theorem. F, right here, here's my F. Here is my G. And F equals G, except that x equals 2. So the limit as x goes to 2 of F is the same as the limit as x goes to 2 of G, which is 1. Except that x equals 2. Right.
Yeah, the limits are the same.
Yes.
Except x equals 2.
No, their limits are the same. Look at the conclusion. Their limits are the same. No exception. You're confusing the condition with the conclusion. The condition is f equals g except that x equals 2. That's the condition. F and g are the same except that x equals 2. The conclusion is their limits are the same. Okay? Good. All right. So that was alias theorem. Now, in addition to a cancellation technique that we showed here, closely related to that was rationalization. And I'm going to let you go find some examples for yourselves. And so that you can practice those. There are some rationalization exercises that I put out a long time ago that you can find if you want to practice them. A relatively uncommon theorem that we use is called the squeeze or sandwich theorem. And the situation there is that we have a function that is sandwiched or squeezed between two other functions, bounding functions. And our picture here is that we have an F, we have an F, we have an H, and we have a G, like so. And in particular, if these two bounding functions both go to the same limit at C, then we know also that g of x must go to that limit at C. For your purposes, if I ask you a question in which squeeze theorem would be helpful, I will provide you with the appropriate bounding functions. So I might give a question in the format, if f is between 4 minus x, 4 minus x squared and 4 plus x squared, there we go, then the limit as x goes to 0 of f of x equals, and I would consider that my bounding functions both go to what value as x goes to 0? 4. And therefore the middle function must also go. So these are the major techniques that we will use analytically. There are two specialized techniques we use for special types of limits. For limits at infinity only, for the limit as x goes to infinity of f, or the limit as x goes to negative infinity of f, we can use n models. So for example, if I need the limit as x goes to negative infinity, that should all be red. I need the limit as x goes to infinity of x squared plus 3x over x cubed. Then I would appeal to the n models here, because for very large negative values of x, x squared plus 3x is basically x squared, and x cubed is of course x cubed. Canceling powers of x, I get the limit as x goes to negative infinity of 1 over x, which is 0. And you recall that these n models, that these limits at infinity give us the locations of horizontal asymptotes. So we can conclude from this analysis that f of x has a horizontal asymptote, HA, horizontal asymptote, y equals 0. Likewise, if the limit as x goes to c of f of x is infinite, then we can use sign analysis to determine whether the limit is positive infinity or negative infinity. So for example, if I wish to find the limit as x goes to 2 from the left of x minus 1 over x minus 2 cubed, then I consider, because I have a fraction here, I check the form, and my form is 1 over 0. And because my form is 1 over 0, the form k over 0 in general is the infinite form. And it tells me that my limit will be either plus infinity or minus infinity. And to find out which, I'm going to simply analyze signs at top and bottom here. And for x is close to 2, 2 minus 1 is 1. So I'm going to get a positive sign right there. For x is close to 2 but less than 2, x minus 2 is a negative value. Cubing that still gives me a negative value, and therefore I have a negative denominator for x is close to but less than 2. And therefore this limit will be equal to negative infinity. Yes, sir? Just from both sides. Well, to find that out, we would need to consider the other side. And if we consider the other side, I think you can do this in your head probably. My sign on the top will be plus, my sign on the bottom is clearly going to be positive as well. And therefore my limit is going to be positive infinity. Because these two limits do not agree with each other, then from both sides I must say the limit does not exist. That's the most I can say. I could also say it is infinite, indicating that I've got a vertical asymptote. Remember that a limit of infinity tells me that f of x has a vertical asymptote at x equals c. So those are our analytic tools for finding limits. There are a lot of them, and so you want to practice doing them. Find yourself some practice problems. A great place would be the end of chapter 2 in your book on limits, and just practice doing limits. Now, what if I want a graphical evaluation of a limit? And I go back to our picture here. If I want a graphical evaluation of our limit, and this is my function f, this is my function g, something like this, then the limit as x goes to c from either side of f of x is equal to L, because for x is close to c, f of x is close to L. But here in the bottom, if I take the limit as x goes to c from the left, then I can use my finger to trace along and see that for x is close to c to the left, then I'm going to get L. But for x is close to c from the right, I'm going to get M. And on the basis of the fact that I have two different limits from left and right, I conclude what about the limit as x goes to c of g? Does not exist. And please notice carefully the notation. This is not equals d and e. This is pronounced does not exist. That limit does not exist. And this is the content of our two-sided theorem. And that is that the limit as x goes to c of f is equal to L if and only if the limit from the left equals L and F of C is in. Yep. So we want to distinguish here between f of x, which is the entire function, and f of c, which is f evaluated at that function. Yes.
So it goes from the distance in the first one.
Yes, it does. Because from both directions, my limit has the value of f.
But it is a whole thing.
Now think about our definition. Our definition of limit, all the way back at the very beginning, is f of x is arbitrarily close to L when x is close to, but not equal to c. So that when I have a function that is close to L, when x is close to but not equal to c, then the limit is L. What happens at c does not make a difference.
X equals C could be L.
Could be, that's right. That's right. If I bring this down and fill the hole, then my limit is L, and now my function is continuous. Yeah. And then finally, numerically, if I need to evaluate a limit on the calculator, on the graphing calculator, then I am going to choose values of x that are close to but not equal to c. So for example, if I wish to evaluate the limit as x goes to 2 of something crazy like e to the negative sine of x or something insane like that, all right, then I'm going to set y1 equal to my function, and I'm going to trace along the graph, and what two x values should I pick in order to estimate this limit?
1.999.
Yeah. Yep. And if these two values agree with each other, that is evidence that my limit is equal to whatever it is. I will not choose x equals 2, because that's not what a limit is. I will choose x's that are as close to 2 as I can get within a 4 decimal place ceiling. By the way, all calculator answers need to be represented to how many decimal places? 4. All right. Good. Good. Well, what can we do with limits? There are essentially 3 different things that are kind of related to each other that we can do with limits. And the first is we can determine continuity. And I need to go back to red here. And we have a definition for continuity. F of x is continuous at x equals c if the limit equals the function value. And so we can use limits to show that a certain function is continuous at a certain point, or at a general point. So, for example, the content of our polynomial theorem, the limit as x goes to c of p of x equals p of c, another way of saying that is polynomials are continuous functions. If we do not have a continuity, then we can classify our points of discontinuity. And tomorrow I will pick up with an example of this, but very briefly, remember that we have 3 types. Removable, in which the limit as x goes to c of f is equal to L, but f of c is not equal to L. A whole. That's exactly right, but its official name is a removable discontinuity. We have a jump discontinuity, in which the limit as x goes to c from the left is different from the limit as as x goes to c from the right. And then finally, we have asymptotic, in which the limit as x goes to c of f is infinite. Now, because we have three kinds here of discontinuity, people are tempted to confuse them with something else that we have three kinds of. What other graph feature do we have that we have three kinds of? Non-differentiability, right? They confuse them with the corners, the cusps, and the vertical tangents. How do I keep those straight? These are not to be confused with the types of non-differentiability because I'm not looking at derivatives. I'm looking at limits. So these are not the three types of non-differentiability. Yeah, technically there are four. A place where f is discontinuous. So yeah, that may help you creating four. Related to classifying points of discontinuity, limits allow me to ID horizontal and vertical asymptotes. And so we had some definitions. Y equals L is a horizontal asymptote. Only if the limit as x goes to infinity of f is equal to L, or the limit as x goes to negative infinity of f is equal to L. Examples of functions that have horizontal asymptotes. Some rational functions have horizontal asymptotes. E to the x has a horizontal asymptote. On the other hand, the vertical line x equals c is a vertical asymptote if and only if the limit as x goes to c of f is infinite. And our last use for limits is to compute rates of change, aka derivatives, but that's tomorrow. Yes?
Vertical asymptote.
Oh, vertical asymptote.
Mm-hmm.
Doesn't matter if x goes to c, that from the left is positive, right from the left is.
You will get a vertical asymptote in all cases, and that's why I didn't put any